Hello, everyone. Hope you're having a good time here at Spark AI Summit 2020. Thank you for being here. My name is Vishakha Sharma. I'm a principal data scientist at Roche, and I will be co-presenting our talk with my colleagues, Yogesh Pandit, who's a staff software engineer at Roche, and Johnson Labs CTO, David Talby. And the title of our talk is Automated and Explainable Deep Learning for Clinical Language Understanding at Roche. In the first part of the talk, we will cover why patients and doctors need accurate and automated natural language understanding at scale. In the second part of the talk, we will cover how we build deep learning, NLP, and OCR models and pipelines that address the challenges. And the last, we will cover achieving state-of-the-art accuracy on real healthcare data in production. Full disclosure, Roche is a happy customer of Johnson Labs. We are co-presenting this talk to give a high-level overview of the Roche use of Spark NLP, a product from Johnson Labs. Nothing contained or stated herein during the presentation constitutes a Roche endorsement of Johnson Labs products. Johnson Lab is fully responsible for accuracy and completeness of any statements related to Johnson Labs products, including the product's performance. To tell you a little bit about Roche, it is a 120 years old company with headquarters in Basel, Switzerland. It has two main business divisions, diagnostics and pharmaceuticals. It is number one in vitro diagnostics and a leading providing of cancer treatment worldwide. Within diagnostics, we are a team called Diagnostic Information Solutions. Our primary focus is the Navify decision support portfolio, where we are working mainly in oncology. Navify TB Tumor Board is a cloud-based workflow product that securely integrates and displays relevant aggregated data into a single holistic patient dashboard for oncology care teams to review, align, and decide on the optimal treatment for the patient. The clinical decision support apps ecosystem is secure and fully integrated with Navify Tumor Board. We have 3 clinical decision support apps: Navify Guidelines, Navify Clinical Trial Match, and Navify Publication Search. For a cancer patient, a large number of data points get generated along their journey. For example, genomics, pathology, radiology, their clinical data. The goal here is to navigate through the complexity of patients' journey and generate a longitudinal view by unlocking these data sources. And for more comprehensive view, unlocking unstructured data is very important because a lot of the time this has diagnostics and treatment information. These data allow us to do clinical decision support and population analytics. For this talk, we are going to focus on the unstructured text data in the pathology. Here is an example of pathology report. Pathology reports are very diverse. They have jargons, tables, key value pairs, and handwritten notes. If you see on the right side, which is a sample report from pathology domain. In a lot of cases, when a sample report gets reviewed by a pathologist, it looks like this. How many of you have seen something like this? This is handwritten text. And if you read closely, you can see they are talking about tumor site, tumor staging, ICD course, and a bunch of other things. All of these annotations make this report extremely valuable. But the challenge is, how do we extract all this information? It is quite clear after looking at these reports that along with NLP, we will need OCR to efficiently extract information. What is NLP? Natural language processing is a field of artificial intelligence that helps computers understand, interpret, and manipulate human language. NLP draws from many disciplines, including computer science and computational linguistics, in its pursuit to fill the gap between human communication and computer understanding. What is OCR? Optical character recognition is the recognition of printed or written text characters by a computer. So we need natural language processing with high accuracy, specialized for medical data, with minimized time to train models, and that can be extended for new content types. We need OCR with high accuracy and ability to retain document structure like tables, lists, and paragraphs. We had a bunch of requirements from tools and services that could help us achieve this task or needs, like scalability, compliance, low cost, ability to run on-prem or in the cloud. The success of NLP approaches heavily depends on being able to understand the domain. And as a first step, we want to identify named entities from the domain-specific documents. These entities are highly specific to the use cases. Healthcare data is extremely heterogeneous and complex and requires high quality labeling data and domain expertise, and that can be very expensive and time consuming for any organization. At Roche, we have extracted more than 45 oncology entities from pathology reports. Here are few examples of a surgical pathology report from patients diagnosed with lung, breast, and colon cancer. The highlighted text shows the entities of interest and its associated labels. The first example shows the diagnostic information of a lung patient: lung right upper lobe lesion, wedge biopsy, adenocarcinoma, moderately differentiated, where lung is the location and right is the laterality, wedge biopsy is the procedure, and 2.5 centimeter is the size of the tumor. And it says surgical margins are not involved. The second example shows the microscopic description of a breast patient. Histologic type is invasive ductal carcinoma with metastatic features. Areas of sarcomatoid carcinoma. Histologic grade is not mentioned, and overall grade is 3. In this sentence, we have labeled invasive ductal carcinoma as cancer type and sarcomatoid carcinoma also as cancer type. And 3 is labeled as grade. So the last example shows the clinical data and pathologic diagnosis of colon patient. Cancer location is ascending colon mass, and final diagnosis says right colon with appendix hemicolectomy, two adenocarcinomas, proximal ascending and distal ascending colon. So if you see this example, you see multiple mentions of type, localization, and procedures. And our approach has been, as first step, categorizing the content broadly and as possible. And this helps us achieve high recall with entity extraction. And we then, in next step, drill down into achieving higher precision by mapping entities to standard concepts. NER is, in simple words, is entity extraction and is a subtask of information extraction that seeks to locate and classify named entity mentions in unstructured text into predefined categories such as tumor site, primary tumor, etc. Spark NLP provides both CNN by LSTM and BioBERT implementations, and we have trained models to extract more than 45 labels from the pathology reports. CNN by LSTM is a novel neural network architecture that automatically detects word and character level features using a hybrid bidirectional LSTM. And CNN, which is the convolutional neural network architecture, eliminating the need for most feature engineering. And BERT stands for bidirectional encoder representations from transformers. Unlike recent language representation models, BERT is designed to pre-train deep bidirectional representations from unlabeled text by jointly conditioning on both left and right context in all layers. BioBERT is the first domain-specific BERT-based model that is pre-trained on biomedical domain corpora like PubMed abstracts and PMC full-text articles. So let me hand it off to Yogesh, who will tell you more about our workflow.
Thank you so much for the background, Vishaka. So let me briefly talk about how we landed on this approach. Let me get into a little bit of a background. So when we started off with a more traditional entity recognition approach like CRF, and it worked really well for us when we had like a small, well-labeled data set. But as we started to expand beyond domains, like from pathology to radiology or to genomics, or as we started expanding beyond cancer types, this approach started to crack. Training was taking much longer. We couldn't efficiently leverage word embeddings, clinical word embeddings, and transfer learning across domains and cancer types was not efficient. So that is when we started to experiment with the CNN-based approach, and it has been working really well for us. We use a Spark NLP-based implementation of it, and we've been able to achieve good results with it. It is also a state-of-the-art implementation based on certain publicly available data sets. So the next component in our workflow is optical character recognition. So Vishaka briefly introduced this, but let's quickly reiterate. Optical character recognition is basically being able to convert PDF or images, like text within PDFs and images, to a more machine readable text. So the goal here has been, like, as you can imagine, right, to be able to consistently convert PDFs to text that are machine readable, that are clean in the domain of pathology and genomics and radiology. So to evaluate a system like an OCR, we used a combination of matrix, starting with character error rate, which is nothing but the minimum number of operations required to transform your reference document to your output text. So then we also evaluated it based on a word error rate, which is nothing but how many words are substituted or deleted or inserted between the reference document and the output text. So as you can imagine, like evaluating based on word error rates, it has its own challenges, like dealing with spacing or like dealing with the lengths of word sequences. So because of that, we also looked into a slightly more advanced metric, which was based on bag of words. So instead of evaluating word error rates, we looked into evaluating bag of word error rates, which is, as you can imagine, just a bunch. It's a multi-set of words, basically. So each of these metrics we measured against a bunch of OCR system parameters, like engine mode, which tells you basically if the document is plain text or it has an image layer on it. Then something like page segmentation mode, which basically tells you if the document has just like a character on it or like a blob of text on it, or does it have tables on it or something like that. And then some other factors like scaling of the layer on the PDF and erosion, all of that. So overall, based on these metrics and against the ground truth that we basically generated ourselves, we landed on a set of values for the parameters that has been performing really well for the data that we have. So this is kind of how we experimented and optimized our OCR pipeline. So the next component within the pipeline is entity resolution. So we spoke about named entity recognition and we spoke about OCR, but with just these two approaches, you cannot get structure out of unstructured text. So what is entity resolution? So entity resolution basically is removing duplicates, normalizing data, disambiguating records that correspond to real world entities across like within your data set, basically. So what you see on the screen is just an example of concepts and the codes for those concepts. So the idea has been that we've been exploring is using clinical word embeddings and the chunks resolved from entity recognition. We try to resolve these chunks to one of the concepts within a standard terminology. So like you would imagine, or like you would have multiple models for your entity recognizers, you would need to have multiple models for your entity resolutions, depending on the terminology that is being used. So now that we've discussed the techniques that are at play here, let me talk about the process. So what you see on this screen is on the left side, we're talking about like labeling data and building the models. And on the right side, we're talking about deploying the models and like serving the models basically. So there are many elements here. So for building the model in an automated manner, we stuck with old-fashioned Jenkins, which we use for orchestration. I mean, the primary reason was this is readily available in our infrastructure. So we stuck with Jenkins. Another choice we made was to stick with Jupyter for of course, for our exploratory analysis, but we also stuck with it to run our pipelines. So what we do is we use an open source tool called Papermill, which basically parameterizes our Jupyter notebooks, and we can just run them as like command line scripts in our orchestrator. So this has made our workflow fairly straightforward. So we did not need to maintain a notebook and then maintain scripts that basically run in our schedulers basically. After that, if you see on the diagram, we use MLflow for tracking our parameters, our performance, and logging our artifacts. So this kind of gives us the ability to compare, pull, and deploy any artifact from any of our historical runs. And after that, we deploy the model basically in a container, which is served through a model server. And then it is served through APIs. So this is more for our sandbox kind of an environment. When we move towards productionizing this, it is a lot more manual because we are in a regulated kind of an environment. So just to continue on the workflow, this is kind of a zoomed in view of what the consumer of all of these techniques, NLP techniques put together would kind of get. So the slide basically tells you like if you have a PDF document, you would need to run it through OCR, which brings you back the text. And if it is not a PDF document, of course, you don't need to use OCR. This text then runs through named entity recognition models. You could have one or you could have many, and that basically fetches you all of the entities that the model predicts. And after you get these entities, you will hit them to mapped terminology APIs, and you basically have them resolved to standard terminology. So there is an edge Lambda that we have in place that basically orchestrates all of this. So the end user only needs to deal with input as a document and output as structured data. So you might wonder, right? I mean, looking at the whole pipeline, how much of code one would need to write to kind of get a model running. So fortunately, it is not a lot. This is a snippet of code from Spark NLP. You can see there's a model being built using BERT embeddings and a much deep learning based entity recognizer. So our pipeline looks pretty similar to this. Of course, there is some boilerplate around it to get things going, but the training of our model is as simple as what you see. So this has really helped us keep things simple, and we've been able to reiterate with changes or experiments much faster. So having said that, so I just want to conclude on this section by saying that this whole NLP process, it has kind of been a journey for Roche. We started from scratch, and we've been working towards expanding to more domains and trying to automate as much information extraction as possible. So we started like Vishaka introduced, we started with pathology, and we're working towards a lot more domains like radiology and genomics. And, we're hoping to leverage what we've learned so far to kind of scale up to this new challenge. So now let me hand it off to David who will tell you more about Spark NLP, which is the tool that we've been using for all of our work.
Thank you, Yogesh, and hello, everyone. What I would like to talk about is Spark NLP as a library, which is, as Yogesh and Vishaka explained, one of the enabling libraries for this project in these kinds of use cases. So we hope that this will enable you to understand how you can best use this for your own projects. For the general case, either if you're working on NLP in healthcare, or if you're really just working on this type of very domain-specific text understanding problems. On one hand, you want to start with state-of-the-art algorithms, models, implementations. But on the other hand, you also know that you will need to train your own to tune it to answer specific questions that you need answered from text. So Spark NLP is an open source library. And its goal is to provide the industry production-grade implementations of state-of-the-art NLP research. So what the team does is reads the latest papers, latest research, tries to reproduce it. Whatever does reproduce and generalize becomes part of the production-grade product. Spark NLP is an open source library for Python, Scala, and Java APIs. It's also an ecosystem and comes with more than 100 pre-trained models and pre-trained pipelines, which you can really just activate with, I think, 3 lines of codes nowadays. And it's a very active community. So there were 26 new releases in 2018, 30 new releases in 2019, and the same pace is continuing in 2020. In early 2019, Spark NLP became the most widely used NLP library in the enterprise. And just a couple of weeks ago, O'Reilly published their 2020 AI adoption in the enterprise survey. And once again, Spark NLP is by far the most widely used NLP library in production enterprise settings. On top of Spark NLP, the product that was used to build this project is Spark NLP for healthcare, which is an extension, which is required because, as I think you've seen here, medical NLP, biomedical NLP is a different problem than general language NLP, all the way down to having different kind of research papers, conferences, different benchmarks to deal with it. So there's a different code base and different set of models that deliver state-of-the-art clinical and medical NLP solutions. And as you can see here, it has the same entire base, which we'll talk about, which you can use for anything else. But then adds healthcare specific, first of all, things like tokenization, part of speech, spell checking, and even sentence segmentation. And then on top of it, recognizing clinical entities, like for example, the oncology entities we saw here, implementing clinical entity linking, so doing the entity resolution, as Yogesh explained, and being able to map an entity to a specific code in a medical terminology, finding that status of an assertion. So it's nice that we can extract the term diabetes, but for most use cases, if we cannot tell between patient is diabetic, patient is not diabetic, the suspected diabetes, or a patient has a family history of diabetes. So if you cannot tell between those 4, it's almost useless to have just the term. If you want to look at patient risk, matching patients to clinical trial, or recommending, as in the case of Navify, the best next action from a clinical decision support set. The other very important features, like de-identification of both structured and unstructured data, as well as the OCR capability, which you have seen here. On top of it, Spark NLP comes with more than 50 pre-trained models. Some of them are embeddings, some of them are NER models, assertion status models, entity linking models. But very important, as you've just seen, is the ability to train your own. Because most often, if you're in a healthcare setting and you're looking at a specific specialty or specific use case, you will want to tune your models to extract specific, for example, specific entities. In this use case, we don't care about symptoms, problems, and drugs. We care about the specific size, laterality, histology of a tumor. And then the question is, okay, how fast can you get to a point where you have a very high accuracy model for this specific use case? So in general, in the design of Spark NLP for healthcare, and Spark OCR, there are 3 main design goals, which are accuracy, scalability, and speed. With accuracy, when we say state of the art, it's not a marketing term, it's an academic term, which means that an algorithm is at the state of the art if it really provides the best accuracy achieved on public academic benchmark in peer-reviewed papers. So basically, this is the best that the research community has been able to produce in a verifiable manner. And as you can see, this is really from a while back. Spark NLP does definitely much better than other libraries, really just by adopting some of the latest advances in deep learning and transfer learning. And on top of it, some of the really new things that have happened in the past 2-3 months. If you look at release, the 2.4 release, the named entity recognition deep learning algorithms was reworked, enabling for larger embeddings. Spark OCR now has 20 different annotators to be able to pre-process an image. So Yogesh mentioned things like erosion, scaling, and now you can also do noise reduction, automated scaling, skew correction, and other algorithms that enable you to improve the accuracy of the image before you try to extract text. Clinical entity resolution now has also been completely reworked to newer and more accurate algorithms. And this has actually enabled adding new models such as mapping to basically larger terminologies like SNOMED, GLOINC, and RxNorm, which are now also available out of the box. 2.5, things that have been added really just a month ago is integrated support for BERT and ExcelNet embeddings, and 2 new tasks for which Spark NLP now delivers really state-of-the-art results as of 2020, which is spell checking and sentiment analysis, which really, because it's trainable, enables also broader emotion detection. In terms of scalability, so Spark NLP is based on Apache Spark, and as such, is the only natively distributed open source NLP library. You can run it on any Spark cluster. Also, one important thing, especially in a healthcare setting, when you're dealing with patient data, using this, it's just a library. So this is not an as-a-service offering. You do not need to send your data to a third party, which creates its own kind of compliance, sharing, privacy issues. You can run it on your own, either on a local machine, on a container, or if you really need to scale, you can scale on a cluster. And the benchmark that you see on the right is just from AWS EMR with really 0 code changes. And this is also this is kind of the whole story behind this benchmark. If you'd like to reproduce it, is available online. Apache Spark really benefits us here because it deals with all the really nasty issues that come with distributed computing, like minimizing shuffling, optimizing caching, minimizing the amount of bandwidth that we use, and really doing execution planning of the whole pipeline before we actually run it. So a lot of work was done with the Apache Spark community and the Databricks team to make use of those and make sure that Spark NLP really squeezes the most out of the hardware to give it. Of course, that distributed computing is not magic, and the speed up you'll see depends heavily on the use case. So if you're doing inference, for example, you're likely to see near linear speed ups. But if you're training, say, an RNN, which is by nature more iterative, then you're going to see sublinear speed ups. In terms of speed, one of the other things that Spark NLP invests a lot in is making sure it's optimized for the latest and greatest hardware platforms, specifically the ones from Intel and NVIDIA. So NVIDIA obviously has GPUs, and it has several generations of them, each adding different types of memory architectures and even instructions. Intel, in the past 3 years, really started releasing chips that have deep learning specific instructions. And one advantage it has, it can use more memory than only the memory on the GPU, which definitely helps in some use cases. So Spark NLP has optimized builds for both Intel and NVIDIA. And this specific use case compares 2 generations of Intel chips and the Tesla P100 from NVIDIA. And in this specific case, for this specific use case, which was training a new named entity recognition model for the French language, Intel actually happened to be about 19% faster and almost a half price on AWS compared to Tesla. So in this specific use case, we don't just use the open source Spark NLP, we use Spark NLP for healthcare. So what we also care about is, okay, how accurate is it for these use cases? And the two most important tasks are recognizing clinical entities. So can we actually correctly extract the entities from pathology and radiology reports? And then can we correctly resolve them to medical terminologies? So clinical entity recognition. So by the way, both of these algorithms have a kind of a different implementation within the healthcare code base, because that's what gets you state of the art within this domain. And as you can see, when you compare state of the art nowadays, it's become really nice. There's the NLP Progress online, which actually would list the papers and the benchmarks and will tell you, what is the state of the art as of today. There's papers with codes, and there are some really nice free websites that enable you to keep track of this space, which is amazing because it's moving amazingly quickly. In the past couple of years, if you publish your own academic paper and you claim that you have a state-of-the-art results, you're likely to be at the top for maybe 8 to 10 weeks, which means that our job to actually catch up with the state-of-the-art really means that we just have to keep running, right, and keep adding new things, just to keep taking advantage of all of this new innovation, which is fantastic. So here you can see some public benchmarks on entity recognition. Which really shows that, once again, this is the next to latest version of Spark NLP, which produces out of the box on public benchmarks the highest accuracy for kind of standard CONLL datasets. And what was important in the Roche use case was not only that, but also the fact that if you contrast, for example, to just only using pre-trained models, Spark NLP is trainable. So what we were able to do here is generate training data using clinicians for specific oncology data, right? And then be able to tune a model, right? So we're still using the same graph architecture. We can use the BERT and same embeddings, but we can produce a highly accurate model for this use case, which is a unique capability. The second important task is entity resolution. And that's another thing that you need to do at the NLP stage, because you want your system to know, for example, that renal failure and decreased renal function are really the same thing. And in healthcare, there are many, many ways to write what is essentially the same thing. So if you don't normalize and if you just use the entities as they are instead of mapping them to standard terminologies, the problem is not just integration with other systems that uses those codes. The problem is that you'll have a much shallower feature space, right? Because really, the way you want to use it is, okay, look, if I know there's renal insufficiency, that increases patient risk. That may imply how I treat them. Okay, and I don't want to deal with 3 different ways to write it as 3 completely separate features that I cannot connect. And that's something that you want to do at the text level, at the NLP level. And this is also something that comes out of the box with Spark NLP for healthcare, but also trainable. So if, for example, if you're looking for specific tumor characteristics, in this case, we can train a model to just achieve those. And here also, you can have public benchmarks on 2 academic data sets, so SHARE and NCBI, and the current numbers out of the box for those. So if you want to learn more, or just try to run this for yourself, one nice thing that's available now for Spark NLP are Colab notebooks. So if you look at those links here, which is basically github.com/johnsonlabs/Spark NLP workshop. Underneath, you have public notebooks. And when you open them on GitLab, there's one button that says run in Colab, and then you can run them within your own Google account. So there's really nothing to kind of install or set up. And it would show you both how to use pre-trained models and then how to train your own models in different kind of cases, which is a great way to get started. Other than that, if you're working in healthcare, definitely consider trying Spark NLP for healthcare. If you're working in another domain that requires you to train your own model, so you're working in legal, you're working in finance, you're working in insurance, the best thing is probably start with the open source library and see really how what's the smallest number of documents and examples that you need to give in order to train a tuned model for your domain. And I think that what you'll find is that number has gone down significantly in the past 2 years with advancements in transformers and transfer learning. If you have any other questions, we'd be happy to answer them. Please get in touch with us. There's a we're always interested and happy to know what people are doing. And regardless, there's a very active community that will most likely be able to answer your questions, whether it's a simple out-of-memory issue or a bigger question on how you would get the use case done. So with that, thank you very much, and we'll be open for questions.